it's essentially the same confusion that Alessia also had, that one can make a statement about stability without specifying to any particular dynamics. And then you seem to say that there's a dynamic independent argument for mass inflation. Is it fair to say that
basically you're joining conditions for perturbation? For example, the two perturbation, the two null direction, basically you have joining condition. There are conditions basically how the energy should be related on the four quadrants that are made. And then you keep just slicing. Of course, that is not the solution of the Einstein equation anyway. So the simple point is that you see that there is a huge back reaction, right? Now, what I'm just saying is that to measure how this back reaction affects the geometry, of course, you need a dynamical equation that we don't have. But the problem I see, that is telling you that geometry per se is a metastable state.
It tells you that I cannot neglect back reaction to perturbations.
Well, imagine, because or you oscillate. What we can do at most, the modified dynamics can make oscillation between that and something else. You see what I mean? So it looks like it's not stable. It's not. It must be a metastable. For example, a possibility advancing one of the recent paper by Rovelli is that this instability of the inner horizon would then be the things triggering the bounds that would basically lead to the bounds without having to resort to the joining of the black hole white hole. Basically, you generate the regular black hole, and then the regular black hole instability generated the antitropic region in the future that is necessary for the bounds. So still, it seems to point toward a metastability of that object. Now you might say, what is the typical time scale of this build-up of the perturbation?
No. Why even does it point towards an instability? It points towards that I cannot no longer neglect back reaction, right? But
it's the same, because at the end it tells you that geometry, is piling up a huge amount of energy. You need to have the full equation to work out where it goes. But it cannot stay that way, piling up a huge amount of energy. Moreover, the typical time scale is set by the quantum gravity scale that regularizes the black hole. So it's going to be, if you can fine tune the scale in such a way that is longer, but naturally would be of the order of the Planck scale. So it is everything very fast. So I'm not saying that is a dead end or that regular black hole are not interesting, but as it is, they don't seem to be the end of the story.
All I'm saying that I believe it is a dynamics dependent statement whether the instability will be quenched or not by nonlinear interactions.
But you're making more than that. You are assuming that this quenching works in such a way to preserve the regular black hole, and that it's more an act of fate than you see. You have a huge instability. You need to change that structure that generates the stability. You have to get rid of the inner horizon somehow. And if you get rid of the inner horizon, basically you're not anymore in what we call normally regular black hole. You have another structure, regular structure probably, but it's something else. So you basically go in, and I believe, as you believe, that the dynamics will somehow take this back reaction and make something of it. But you need to basically avoid this piling up. You need a way out. So it seems to me that if you get rid of this unstable structure, which is the inner horizon, you're in something else, which is not the standard regular black hole, which doesn't mean that it cannot be a metastable state, something which is something you go through to go somewhere else.
So you said the argument essentially is that since anything that I can write down in spherical symmetry still has an inner, and is a regular black hole, still has an inner horizon, it will have to evolve away from that further.
Mm-hmm. Exactly. Okay. You need to, and the point is that it's model independent. You do Dimichova You do highward. I mean, anytime you have the inner horizon, you get this problem. You may have different way. You can be that, I mean, now there are subtleties in the sense that you can have an exponential phase and then something that is more tame, but that is always happening after an exponential phase, which in a very short time scale brings you to a huge back reaction. So then you need to know where you go. And there you need for sure the dynamics to say that.
So there are quite a few hands raised. See if they are related to this topic, please go ahead. Otherwise, we wait. Yeah, Astrid, please.
Yeah, so I was just wondering a little bit more about the assumptions that go into what you're saying, Stefano. So the dynamics to understand the back reaction is one thing, but there's also the dynamics that ultimately describes, I mean, that gives you the geodesic equation when you're first tracing the perturbations, right? So for instance, if you're assuming that you have large non-minimal couplings or some other things that modify the standard geodesic equation, will that impact your analysis? I mean, this conclusion that there is large blue shift, or is there a way of modifying the dynamics even at an earlier stage to avoid the large blue shift?
We've done the calculation in two ways. One with the junction condition, like in the with basically the static configuration where you have an inner horizon and then behind, for example, you can have a de Sitter region. And we have done it with the idealized metrical Laori, so in a more dynamical way, but we always get the same result. What you are saying is that you see, I don't think, okay, we haven't done any possible calculation with any possible variation of the team. So I cannot say, but what I want to stress is that the nature of this instability is very clear. It is the structure of the inner horizon. So you may for example, change the time scale. You may add interaction to complicate things, but at the end, you will have this perturbation piling up there anyway. You see, and that is the key of the problem. So I don't think that anything you may do with the interaction or changing the geodesics will do has to do with the causal structure, and that is the problem there. So I don't think that there is anything that can ameliorate the problem. But this is not a bad news, because it shouldn't be attached to idea. Regular black hole, if they are transients, if they are metastable state, this is good news for phenomenology. It's not bad news. It means that they can go in one of the other situations that are very good for phenomenology. And in any case, they are problematic. I think Alessia at some point was citing that in some limit, the temperature was going to zero. No, they don't, it's very difficult to see how they can completely evaporate. That makes the things, there were arguments by Hawking why you wouldn't have like to have remnants if you think that CPT in quantum gravity works and so on. So I don't think that there is anything wrong with I think that is very robust and is related basically at the causal structure. The only way I can see you can make things different is really you affect the causal structure. Go, for example, in Orava gravity, then things are very different. And then that is not so clear what may happen. Right? But that is because you are really going away from relativistic physics.
Yeah, I see the point. I think I'm just wondering about sort of the reverse logic. So if the generic situation, if that has an instability, but there are some very, very specific choices that you can make to avoid that, that is of course highly interesting, because then that is a highly predictive scenario, right? Then that's a way of potentially singling out one among the endless possibilities for modified gravity. So in that direction, I think it's quite interesting to try to understand whether there's ways of going around the assumptions that generally.
I think you can fine tune the problem. You can fine tune the problem.
And I think that's interesting to do, because that
gravity
might give you a way to guess a dynamics that is sort of better motivated than many other gravitational dynamics.
Generally, as physicists, we don't like fine-tuning. Of course, you can run the argument in another way. You say what is down from low energy physics might look like a fine-tuning. From quantum gravity point of view, was the only possible endpoint. That's something that I'm ready to accept. But you need some strong argument. But of course, you can fine tune the surface gravity of basically the kappa minus of the inner horizon to be very, very, very small. I mean, you can fine tune it.
Okay, so Charlie Robson, please.
Hi, I have a quite a naive question for Dr. Liberati. So in the bouncing geometries, what is it exactly which is bouncing? So could you say some more about these type of spacetimes?
Okay, from the point of view of the local causal structure, basically it corresponds to the situation where you have a trapping region and then the future an anti-trapping region. Normally, they were advanced with a very simple idea. Basically, you want to have time symmetry. And so what you do is that you take the collapse diagram of a black hole, and then you glue the singularity region with the white hole corresponding diagram. So basically the time reversal of it. And you glue the quantum gravity region, assuming that there is some non-zero tunneling probability from one state to the other. If you're worried about the fact that you need to go from trapping to anti-trapping, of course, there what you need to glue is, basically what you need to assume is that due to quantum gravity, basically you have that your light cones that before were oriented toward the singularity, now they do this. This basically switching of the light cones can be generated, okay, then we enter in model dependent things. But for example, in some model where you see this, you have basically a shock, which is something like violating the dominant energy condition. So it's superluminal. And it's basically opening the light cones in front of the matter that then bounces out. So also the matter, of course, if you were asking me what it bounces, in the end is the matter, but you need to reverse, to open up the trapping region in anti-trapping region. And that is what quantum gravity is supposed to be. Unfortunately, to my knowledge, there isn't a detailed quantum gravity. There have been attempts to do quantum gravity to do that, but there isn't, a really fully consistent calculation, because you would need that to be able to do a fully consistent calculation for quantum gravity. It's more at the moment we don't have that technology, but there are hints that it can happen, and the estimates are all pointing, in spite of previous initial claims by some group, toward the timescale of order n. So fast bounce. And this is why I'm thinking, I mean, very many people are thinking that might be the bound. There are two possibilities. One is that the bounce happens, but after a very long time. For example, some papers by the group led by Rovelli are basically saying that the bounce happened at the end of the evaporation, because basically it's only there that you have the Planck scale condition again. Other ideas is that it's fast, but it's asymmetric. So you have these multiple bounces that then stabilize toward the compact object. If you may wonder why this is possible and not possible with a simple collapse, the very simple argument is the following, that if you start with Minkowski vacuum and you do a collapse, there is a theorem telling you that if the state is Hadamard, it remains Hadamard if you don't have a Cauchy horizon in your history. That implies that you can keep renormalizing the space energy tensor as you climb the collapsing star, and you expect to have a small correction with respect to flat space-time because you are free falling. The only way this correction can be important is that if you're not free falling. So, or if the star fight until the very end, the collapse, but then it's unclear how you can make this generic, because you can have very large bodies which reach very low density before crossing the horizon. Or you have that you reach Planck density beyond the trapping horizon. There you have a bounce, but then the bounce stops every time closer and closer to the would-be horizon. When you stop, you are very far from free falling, and then you may have an effect of vacuum polarization that built up. So this is an alternative picture. I'm not saying that this is more plausible than a simple bounce, but is a way in which the bounce could end up in an ultra-compact object supported basically by the Bulwer state. And there are static solutions that can describe the endpoint of this process.
I see.
Thank you. But we don't have a dynamical model, to be fair. And this is what I told you is a story. It's not a full working model. Yeah.
Okay. Okay, thank you.
Shinji?
Yes, I'd like to ask a question to George, if I may. And
Okay.
Yes, thank you. Yes, so in general, in quantum gravity, is it possible to justify this symmetry reduction, or namely of course, I mean, ideally we want to quantize the whole system and then go to the say spherical symmetric case or say cosmology, but if we start from classical theory and reduce the system to the symmetric case, say spherical symmetry or Friedman, then the quantize, and I think symmetry reduction and quantization do not commute in general. And in some cases, maybe we can justify. But so do you know how? I mean, in which case we can justify?
There is a message for you. Sorry, go ahead. Go ahead. Sorry, is that the question? Or?
Yes. How to justify symmetry reduction in quantum gravity?
So there are two things. One is, as you said, some people, including myself and others, first reduce classical and then quantize the resulting system. Other people are trying now in loop quantum gravity to take full theory, take states in the full theory that are symmetric in some way, and study the evolution of those states. And ultimately, that is the way to do it. And so the way to validate studies of the first kind, studies that first reduce and then quantize, is ultimately by, in the full theory, finding symmetric states and show that that dynamics that you found there is what this generates. And there is some partial results for that. I mean, people like Andrea Dapor and others have been looking, particularly in cosmology, in looking at the full theory, states that that are homogeneous, and they show that the dynamics that they get indeed is similar to the dynamics that people found in loop quantum cosmology, where one first reduced and then quantized.
I see. So
there is some progress in that direction. Of course, not everything can be done. They also have done it for spherical symmetry as well.
I see. Yes. So in general, we need to do the both analysis and then compare.
Well, normally the first analysis is much easier to do, so it's what people do first. But that's what I emphasize in my talk. These analyses can never be the final word on something. They have to be validated. Okay.
Yes. Yeah. Thank you very much.
Raul?
Yes. So I have another question for Jorge.
Go ahead.
I know that you have stressed that so this what you were doing is kind of a toy model in the sense that, as you were saying, so you need to validate this. But I was wondering about the ingredients that this approximation or toy model can capture. In particular, if we do if you do the process of just applying this polymer scheme, right, and before doing anything, you may expect that this may be able to, for instance, avoid singularities, right? I don't know.
Yes.
It's like when you do a simulation, you see that that's not the case, right? So
yes.
I mean, is that so in principle, the polymer scheme that you applied could be enough to avoid singularities, right? But
it could be. It's not something we have focused on this piece of work, because this code of Chopwick only covers the exterior of the black hole, so it is not in penetrating coordinates. But yes, people have in other studies studied the polymerized equation and show that the singularity disappears. But again, all that has to be validated ultimately. In loop quantum cosmology, it has been validated. I mean, people know how to do the states, do the full quantization of the model, not the polymer, just one, and show that what the polymer theory was giving you is correct.
Mm-hmm. Yes, but so I mean, I was going in the direction that even if, as you were saying, you need to validate this, but only if you're able to construct some equations that lead to non-singular behavior, even if they are not ultimately linked to a particular theory of quantum gravity, I think that would be very useful, right? Because
so there are several of those.
Yeah. Okay. But applicable, so it's like, are they in a situation or is it possible nowadays to do, for instance, full numerical simulations of these equations, or there are technical issues?
No, they can be simulated. But again, as a professor of mine used to say, do you want to put a Ferrari engine in a broken old car? No. I mean, if your equation is already a suspect from the beginning, you shouldn't keep on pushing them beyond their limits. Right?
Okay, yes, I understand. Thank you.
Okay, more questions? Okay, in the meantime, while people obtain or get more questions, I would like, Stefano, perhaps you can comment a little bit on I mean, you've got a compact object, and so you expect echoes from that compact when you've got spiraling or whatever situation. But what I would expect is that the presence of those echoes or something will depend on the reflectivity of the surface in which of the object that you have. But not only that, but I would expect that coefficient of reflection would depend on frequency. It would be spectral probably. So again, echoes are slightly more difficult to predict because perhaps the spectrum is not adapted to the waves that you are sort of.
Yeah, I totally agree with what you say.
So
no, I totally agree. I mean, I didn't quote even the frequency dependence.
May be strongly model dependent, right?
Yes, absolutely, absolutely. So you need. I made just a comment about what we can say just because we know that the object. I mean, that if the object, whatever it is, must be stable or at least very difficult to destroy. Otherwise, there wouldn't be a good black hole mimicker, right? So my comments was simply that that per se is telling you that this object must be very efficient in absorbing these fluxes and transforming them and adjusting to them, right? Now, the other point that you make is that not only the absorption should be efficient, but it could be frequency dependent in a way that is very difficult to predict without a model. And it's very difficult. Yeah, I've thought about this problem. I was also wondering if one can have some reasoning about, for example, if it is more transparent in the UV with respect to, if there is a plasma frequency for a quasi-black hole, right? That they have to be transparent beyond some frequency. But I find very hard to find the kind of generic argument guiding you in this. Say that, I agree with you. The absorption, there is no reason why it shouldn't be frequency dependent, apparently, given that is involving the matter that is making the object, right?
But I would make it a bit hopeless just to pursue that, in the sense that I think it would depend very much on the model that you're considering, the kind of matter that you have.
Yeah, but then what we should do, we should abandon the study of echo, which at the moment seems to be the most promising channel in gravitational waves to probe this object. I would say that you can model, you can basically try to model the absorption coefficient, which some people has already done. But then you can also insert this frequency dependence, and you can model different, way the frequency dependence work. For example, it is a filter that selects only the infrared. It is a filter that selects only in the UV. That is things you can play with, and then you will see how the waveform are affected. And then you may do searches, blind searches, and find you may find that there is some typical signature, right? Of course, we may be unlucky, and in some model you get that the quasi-black hole is transparent exactly at the frequency typical of the way gravitational waves produced by the emerging then tough life, But I would say that I agree on one side of you. On the other side, I don't think that this should discourage us from exploring better this channel of the echoes and understanding what are the possibilities.
I agree. That's clearly a promising channel, so we should pursue it. So I agree. More questions? Raul?
Yes, my question is for Alessia. So it's about essentially how difficult do you think, or how far away you think it's including time in your calculations? I think in the first, like in the self-consistent renormalization group approach, that would be probably more difficult. But in the second part of your talk, in which you had effective actions, it may, I mean, perhaps not having not exploring full time dependence, but one can study, for instance, perturbations, right, on top of these geometries once you know that they are solutions. So I don't know what you think about that.
So the second point, so that with the effective action, if one has it, it is doable in principle, but the field equations will be really, really, really tough to solve, especially that one would expect to have no localities at the level of the effective action, and the field equations are so from what I have seen, for instance, in the paper or from the local gravity community, one can solve that equation only in some limits that are also not the interesting limits. But regarding the first point, so the normalization group improvement, so there is a work that I have done before, so some years ago. So before I tried to implement this iterative procedure. So it was the first step, normalization group improvement, and it was done for a system collapsing. So there is a time dependence. It was a simple one. It was just a Bayesian model where the mass function, so it was essentially linear with the advanced time. It was called the Kuroda-Papapetrou model. And with that, you can also indeed perform the same procedure. But so what I did at that time was first step, RG improvement. And what one gets is a black hole with one single horizon, but integrable singularity. That is interesting in the sense that once you put some dynamics into the systems and matter, things could change. And a natural thing to do would be then to combine that model, even if it is simple. We don't really know how the collapse takes place, but I mean, there are some models that one can play with. And combine that with the iterative procedure to see if this thing of the integrable singularity is stable. But that would be, I think, nice also to evade some of the assumptions of the papers that you, Stefano, Francesco, and collaborators have put forth.
Okay, thank you.
So we are nearly the end, but I see, of course, we are here quite a few people working on quantum gravity, on black holes, the singular or regular part of black holes or whatever. So I would like to pose a question, which is an old question, but I think it can be renewed continuously. And it is the following. I mean, quantum gravity, we know it's elusive. I mean, we've been for years trying to do so, more or less with moderate success at best, right? So, however, we keep using, when we're doing black hole physics of the kind that we're discussing here, we keep using expressions like the quantum theory of gravity will help or do this, and ultraviolet completion of gravity will do whatever, and so on, concerning singularities in particular. So we always face the issue that all these ideas are model dependent again. So I would like to pose the question, do we have now some expectations or some features that we expect that will be common to all or most theories of gravity, so that they will survive to the final theory, and some others that we know that are model dependent? So perhaps for doing this sort of thing, since we don't have a quantum theory of gravity, it would be good to know which features would be expected to have and to rely on, despite we don't have the theory of gravity. So maybe some of you can comment on that. Stefano.
To me, the answer is that, for example, I mean, you see, we know that they will do. The problem is that the quantum gravity, whatever it is, should be consistent with the possibility to know reality. But you say, okay, But this is a philosophical, but it's also based on what we always see at work. When we didn't know a theory that was completely our knowledge, and it then always end up being a predictive theory. So for example, to me, if quantum gravity doesn't solve the problem of Cauchy horizon, it's not quantum gravity. It's really not useful. Why Cauchy horizon are even worse than singularity? Because Cauchy horizon, for example, are chronological horizon, could be chronological horizon, and you have logical inconsistencies. Now you have to modify, of course, you can modify your description of reality to allow for, a multiple universe and so on. You can always accommodate, but then I still think that the chronological protection conjecture is the most natural resolution of that. And that should be enforced by quantum gravity. That we know is a solid result. There is a K-Radikowski-Wald theorem that tells you that the two-point green function fails to be Hadamard than the Cauchy horizon. So you fail to be able to renormalize. Quantum field theory is not going to give you the answer. Quantum field theory in curved space-time cannot really be the definitive answer. So we know that quantum gravity has, for example, some tasks. So independently from what quantum gravity will be, we know that what we call quantum gravity should do that. So I think it's legitimate that you work using what you know that in the end will do, and work out what it can tell you, for example, on the structure we see in the sky. So, on the other side, of course, what you're saying is totally true. We don't have a working model, and maybe we will have one. We will see that some of the conjecture about, they define things that quantum gravity, but I'm pretty sure that once we will have it, you will see that there are no time machines in that universe that are solution of the full quantum gravitational regime, that there are no lack of predictability, that you can carry on your Cauchy problem. You just have to transmutate, to use the full theory to solve some problem, not to. And maybe the notion of causality change, right? Because maybe you have an emergent space-time, and so you must have. But that doesn't matter. It doesn't mean that the things that are generating obvious problems in the actual theory, predictability, should not be removed. And that is, I think that's something what we call quantum gravity should do.
Okay. Any other insight, or yes, Astrid?
Yeah, just to add a slightly different point of view. So I mean, I fully agree that Cauchy horizons are quite problematic, but nevertheless, it's quite interesting that regular black holes have now been motivated from a number of different approaches. So from asymptotic safety, from loop quantum gravity, there are also arguments from string theory. And I think we should, whenever we have this situation that different quantum gravity approaches give rise to sort of similar structures, we should take that much more seriously than we are currently doing in the quantum gravity community, and really think more about how to connect those objects potentially to something that is testable or not. And I think this fact that these particular black hole metrics have come out in a more or less universal way, I don't think that has been emphasized enough, and that is actually quite a remarkable result, because it comes out
also
from
bounces.
It comes out from theories that on the face of them, they look quite differently, and they start out from quite different assumptions. So I think maybe to be able to answer such questions better, what is quantum gravity telling us about black holes and so on, we need to get used to work more together across the approaches in quantum gravity. I don't think we are doing that enough. Yeah. So that's maybe more sort of
I
a task to us to how to actually get to the answers to these questions. I don't think we can do that by staying in our separated camps, and we should jump on these opportunities when we see something common emerge.
Yes, I agree as well. But for instance, it seems like most of the models that you've mentioned and that we are considering our regular black holes assume or seem to imply that quantum gravity must have a repulsive regime. So can we take that as a
prediction
starting point?
I mean, yeah, sure. Why not take that as a starting point and then sort of see where that leads us, right? I mean, take those points of convergence really seriously and start to think further from them.
Yeah, but you know, David advocate could say that we are putting in this, given that we don't have the theory of quantum gravity, we are somehow putting our bias, some priors in the derivation we're acting, you know? And that is, I think is true for all quantum gravity calculation that we have so far. So for example, sometimes they lead to bounces because they have different priors, they don't lead to, and anyway, Cauchy horizon and inner horizon are not exactly the same thing. We have to be careful because the two problems are related, but they're not exactly the same problem, right? So just commenting. I think there is Francesco with the rise hand.
Yeah, no, I just wanted to just a very small comment because I completely agree with what Astrid was saying. But on the other hand, I also think that all these theories, all these works, they are doing some similar assumptions. And so, for instance, from what Stefano was saying, we can see that there are not actually many possibilities. So once that we assume that you are going to have a geometry, you start with a static configuration and you try to regularize the static configuration. And with the topology that you have at the beginning, actually regular backcore are the only possibilities, at least spherically symmetric situations. So it might be that we are actually putting the same ingredient in all these approaches of quantum gravity. So maybe, for instance, if we start from a collapse, as Luis was saying, you will not get a regular backcore, you will get a bounce. But if you start from a static Schwarzschild geometry, actually, once you regularize it, I think that's the only possibility that you can get is a regular backcore because of the geometrical analysis that Stefano was describing before. There are no other classes actually.
Okay, I think we are like quite a few minutes over time, so I think it's time to stop. I'm sure that all these questions, topics, and so on will be further discussed in great detail in the workshop, in the forthcoming workshop. So thank you all for participating and see you tomorrow.